Hello, this is Jack Jackson. We're going to start a series of lectures on rational relations, rational expressions, and along the way we're going to be reviewing rational numbers and some of the operations and expressions there, and see how that translates to rational expressions. And so recall that rational numbers are the quotients of two integers. In other words, a fraction with integer numerator and denominator. Well, rational functions are fractions with polynomials for numerator and denominator, or at least that's a rational expression, and then y equals that would be a rational function. And so the basic algorithms we have for manipulating rational numbers, fractions, in other words fraction operations, are exactly the same algorithms, procedures used to manipulate rational relations. So we're going to start by reviewing these. These are from, well, the rational number operations and concepts really go all the way back to elementary school. Rational number operations, so our elementary and junior high school topics. The rational expressions are covered in intermediate algebra, and so we're going to go over those. So again, rational numbers are defined to be numbers of the form p over q, where p is an integer and q is a natural number. So they're the quotient or ratio of two integers, fractions. We got to make sure that the denominator is not 0. Remember, we don't divide by 0. And it turns out, first of all, that you can take any fraction and convert it to by long division, convert it to a decimal form. That decimal form will either terminate or repeat. When I'm talking about fraction, I'm talking about these kinds of fractions with integers for the numerator and denominator, non-zero denominator. Conversely, we can go backwards and take, if it's a terminating decimal or a repeating decimal, we can convert it back to fraction. Now those are different processes. Let's just kind of go over those processes real fast here. So we see that what we have here is a long division algorithm. So you got 5 over 8, that's 5 divided by 8. You line up your decimal point and say 5 divided by 8 is 0. Then you go 50. 50 divided by 8 is 6. 6 times 8 is 48, which is really 4.8. And then subtract, you get 2. And bring down a 0, that's 20. It's really 0.2. And then 20 divided by 8 is 2. 2 times 8 is 16. Subtract, you get 4. Bring down another 0. 40 divided by 8 is 5. 5 times 8 is 40. Subtract and get 0. So if you ever get a 0 remainder in this process, we have a terminating decimal. So this is going to happen exactly when the reduced fraction has a denominator that's only built up out of multiplying a certain number of 2's and 5's. 2's and 5's are the factor of our base. Okay, if it's got any other factors besides that in the reduced fraction version in the denominator, it will repeat, like this one over here. 35 over 11. 35 divided by 11 is 3. 3 times 11 is 33. Subtract, you get 20. 20 divided by 11 is 1. Times 11 is 11. Subtract, you get 9. Bring down a 0. 8 times 11 is 88. Subtract, you get 2. And notice that 2 matches what we had before. So the next one's going to be another 1, and then another 8, another 1, and 8, 1, 8, 1, 8, 1, 8, 1, 8, forever and ever and ever. And so we say that's a repeating pattern, which we indicate with a bar. And there's some for you to practice. So this is, since this is review material, I'm going to kind of go through this fairly quickly. So here's some examples of a decimal to a fraction. So a decimal, you write the number in the numerator without the decimal point, count how many places to the right of the decimal you are, and that's how many zeros will be after the 1 in the denominator. In other words, 10 to the third power is in the denominator. And then you just reduce that fraction. So the denominator is always just a power of 10 on the terminating decimals, and then you reduce it. Okay, so pretty straightforward there. That works even if this number is bigger than 1. This will give you an improper fraction here. But this is a reduced improper fraction. So there's some examples for you to practice. Now, the repeating decimals, here's a step-by-step written out. Right, let x be the original number, multiply both sides of the equation by a power of 10. Okay, the power of 10, the number of zeros, will be the same as the number of digits in the repeating pattern. Okay, this will move the decimal to the right on the constant side of the equation by that many digits. Line up the decimals and subtract your original equation from the one produced in step 2, and the infinite tail will cancel out. Now, if you still have a decimal, multiply both sides by a power of 10 to remove the decimal. Then divide both sides by the coefficient of the x, and you've got a fraction form, then reduce it. So let's see how that works. Some examples here. Let's start with this one. 0.3 repeating. Make that a little bit bigger so you can see it better. Okay, well, so suppose we start with that. We don't know what fraction it's going to be. So let x be the 0.3 repeating here. Then what we do is we multiply. There's one digit in the repeating pattern, so we multiply both sides by 10. So then it gives us 10x, and then this gives us 3.33333 repeating. Now, subtract the original one from the other one, from the new one up here. So notice these are lined up in such a way that that infinite tail lines up, and when they subtract, that cancels out completely. And that just leaves 3 on the right. So we've dealt with the major problem, which is getting rid of that infinite tail, that repeating pattern. Now on the left we have 10x minus 1x is 9x. Divide both sides by 9, we get x is 3/9, which reduces to 1/3. And of course you could check it by dividing this out, long division, converting back. So look at the next example here. This one has a 2-digit repeating pattern. So what I do is I multiply by 100. Notice that's going to take this decimal, move it 2 places to the right. That's going to be 23.13131313. Notice I've noticed that all these infinitely many 1-3s from this point on, from the 3rd place on, are going to line up. So when I subtract, that part cancels out. What's left here? Well, let's see. 23.13 minus 0.23 is 22.9. And 100x minus 1x is 99x. Now we still have a decimal. Well, it has one place there in the decimal, so we're going to multiply by 10 to the first power, or 1 with 1 0 after it, on both sides. That's going to move the decimal over here, get rid of our decimal. Of course, that's going to multiply this by 10 as well. Now divide by the coefficient of x, and there's our fraction. What? That's upside down. That one should be on the top. This one should be on the bottom. And I don't think that reduces, so there's your answer. Okay, let's look at another example here. So we get all these back on one line here. Okay, this one has a 3-digit pattern. So we're going to multiply by 1,000. Of course, that gives us 1,000x on this side. And more importantly, over here, it's going to multiply by 1,000. It's going to move it 3 places. 1, 2, 3. 202 point. Then what's next? A 1, 3, and then a 2, and a 1, and a 3, and a 2, and a 1, and 3. And if you notice from this point over, the 2 1s and 3s line up. So when I subtract, all that infinite tail cancels. So the infinite part is the difficult part. It's gone. So now we have 202.13. We subtract 0.20, and we get 201.93. There's 2 digits here, so I multiply by 100 to clear out the decimal there. And then, of course, that gives me 99900 times x. Divide by that, and we get this fraction here, which reduces, looks like I could cancel the 3 out of the top and bottom there. So here's some for you to practice. Okay, next I want to talk about another important thing from arithmetic, is the greatest common factor and least common multiple. And to get at that idea, let's go over a few basics before that. When you have natural numbers, okay, a factor, when you multiply two things together, a times b equals c, then a and b are called factors of c. C is called a multiple of a and b. Now, one of the things that you can do is you can break numbers into prime numbers with a prime factorization, and that's going to be the key for finding greatest common factor and least common multiple. So for greatest common factor, what you could do is actually list all the factors of the numbers, although they could be many factors, and then find which ones are in common, and then find the greatest of those things. That's what greatest common factor means. Another word for a factor is a divisor, so this is probably very often called the GCD, greatest common divisor. Least common multiple, you can't really list all the multiples because they're infinitely many, but you can list them until you find a match. That least common multiple will be the one you're looking for. But it turns out you can do this very nicely and easily from looking at the prime factorizations. Fundamental theorem of arithmetic says we can take a natural number and break it down into a product of prime numbers. Remember, prime numbers are numbers which have exactly two factors, the number 1 and the number itself. 1 is not a prime number because it only has one factor, which is, of course, 1 in itself, but that's only one number. Composite numbers have 3 or more factors, more than 2. So here I did a factor tree, and I broke this down, and I saw that 13,608 equals 2 cubed times 3 to the 5th times 7. 3,600 is 2 to the 4th times 3 squared times 5. 13,608 is 2 cubed times 3 to the 5th times 7. So regardless of how many different ways you might do this factor tree, which there are lots, when you get to the end, if you group the prime number bases together and put them with an exponent and put the bases in increasing order, then there's only one way to write out the prime factorization, and then we have it here. Now, to find the greatest common factor, the way to do it is take all the bases that you have and use the least power that you see. Okay? So, let's look at this. The base of 2, we have powers 3, 4, 5. We go with the smallest power, which is 3. The bases of 3, base 3 here, we have powers of 3, 2, and 5. The smallest power is 2. For base 5, we have powers of 1, 2, and 0. The smallest is 0, so that doesn't show up. 7, we have 1, 0, and 1. That's 0. And anything bigger, they're all 0, so they are zeros. Of course, the ones with 0 power you don't have to write down. And so the prime factorization of the greatest common divisor is 2 to the 3rd times 3 to the 2nd. That's 8 times 9, which is 72. You can also get the least common multiple from this pretty easily. You take all the bases and you use the highest power you see. So the powers are base of 2, the powers are 5, 4, and 3, we go with 5. For base of 3, the powers are 3, 2, and 5, we go with the power of 5 there. For base 5, the powers are 1, 2, and 0, we go with the power of 2. And on base of 7, the powers are 1, 0, and 1, we go with 1. Everything else is 0, doesn't show up. So you multiply all those together and you get this 1,360,800. And so this gives you a guaranteed way of finding the greatest common factor and the least common multiple, and it's a nice way to do it. You might do it by just listing these things out. That works pretty nicely if it only just has a few factors. But when they have more and more possibilities here, it's easier to do it this way. Now, so that's arithmetic. That's elementary school stuff. Now, let's get to some algebra. When we get to polynomials, we use exactly the same steps. So when factoring out means now factoring into prime polynomials. And at this point, we're talking about factoring over the integers. We've talked before how whether or not something will factor depends on what we allow for coefficients. Here we're talking about starting with polynomials with integer coefficients, and the factors will have integer coefficients as well. And if you do this, you get instead of prime numbers, you can get prime polynomials. And again, there's just like in the arithmetic, for the numbers, there's only one way to factor these out into prime polynomials. And we can use our techniques we discussed in our last section. Okay, so if we've got three polynomials here and we want to find the greatest common factor and least common multiple of them, what do we need to do? Well, we need to find their prime factorizations. So here we factor this out. And the first one we can factor out a common factor of 3, leaving me x squared plus 4x plus 4. That's a trinomial square, that's x plus 2 squared. The next one we can factor 6 out, leaving x squared minus 4, which is x squared minus 2 squared, so it's x plus 2 times x minus 2. And notice I also took the 6 and broke it down as 2 times 3, just like I did for the in the prime factorization of the constant factor in the front. Similarly, the next one is factor out of 6, which is 2 times 3, and the other factor is 2x squared minus x minus 10. We use the trial and error or anti-FOIL factoring and find that as x plus 2 times 2x minus 5. So what's the greatest common factor? Well, let's go through the constants first. Prime numbers of 2 for the base, powers of 0, 1, and 1. We go for the smallest, which is 0, so 2 doesn't show up. How about 3? 3, the powers are 1, 1, and 1, so we go the smallest of those, which is 1. So that's 3 to the first power. X plus 2, the powers are 2, 1, and 1. We go for the smallest power, which is 1. How about x minus 2? Powers are 0, 1, and 0, so that doesn't show up. And because the smallest of those powers is 0, and 2x minus 5, 0, 0, and 1, so it doesn't show up. So it's the greatest common factor in factored form is 3 times x plus 2. The least common multiple then would be go with the biggest powers. So we go with the power with base of 2, 0, 1, and 1. We go with the biggest of those, which is 1, so we get 2 in here. And the powers on 3 are 1, 1, and 1, so we go with 1. So this should be a 2 times a 3, which I'm going to go ahead and just write as 6. X plus 2, we see powers of 2, 1, and 1. We go with 2, which is the biggest of those powers. And x minus 2 and 2x minus 5, the biggest power you see is 1. And so there's the prime factorization form, at least on the polynomial part, it's in primes, of the least common multiple. So here's some problems for you to practice with that. Now let's talk about reducing fractions. Okay, well, reducing fractions is turns out to be really basically like just like factoring and canceling is all there is to it. So if I have something big here, I think maybe are these some of the same numbers I used up above? I think those are the same numbers I used up here in this example, maybe. Maybe not. Okay, so I take these things and factor them out. Okay, and we're using a fundamental equivalence property of fractions. It says if you have say x over y, if you take x times a over y times a, as long as a is not 0, these are equal to each other. So that's one of our fundamental defining things about fractions. So these, if they're factors, this will cancel out. Of course, it's also equal to this, another way to see it, which is multiplying by 1. So we're removing a factor that equals 1. So these will cancel out. But only if this is all multiplication here. Okay? So we're going to basically use that property, but the thing is to get it to be all multiplication first, which is a prime factorization process. So we take 13,608, do our little factor tree, we get 2 cubed times 3 to the 5th times 7. Take 99,792, that's 2 to the 4th times 3 to the 4th times 7 times 11. Then cancel out like factors. These 2 to the 3rd cancels with 3 of the 2's in the bottom, leaving 1 2 in the bottom. All the 3's cancel except for 1 in the top. All the 7's cancel, and then 11 doesn't cancel. So now we have a prime factorization form. You can see that that is a reduced fraction in factored form. In the case of the constants, we're going to go ahead and multiply that back out and make it 3 over 22. It's exactly the same steps for working with polynomials. In the top, first of all, we write in decreasing order, factor out a -1. That leaves us x squared minus 4, which factors as x plus 2 and x minus 2. The bottom is a trinomial square, so that's x plus 2 squared. The x plus 2's cancel, and you get -1 over x minus 2 over x plus 2. As long as the thing we canceled out was not 0, these will be equal to each other. Okay? Multiplication and division of fractions is really no more problem than reducing fractions. Okay? Because if you remember, okay, here's some examples with constants, some more examples of just a couple examples of just reducing fractions. But when we multiply two fractions, remember our basic setup is a over b times c over d is a times c over b times d. So if you basically then you want to reduce this fraction. So if we just make sure that when we rewrite a over here, we write it out in prime factorization form. When we rewrite c over here, we put it in prime factorization form, and same for b and d, then we can cancel things out. So basically you just want to the steps are basically just factor, rewrite as one fraction, and then cancel out, and then that's going to be reduced. So let's look at number 3 here. 70 is 2 times 5 times 7, and 121 is 11 square. 22 is 2 times 11, 25 is 5 square. Now we just cancel out. The 2's cancel, one of the 5's cancels, leaving a 5 in the denominator. The 7 doesn't cancel. One of the 11's cancels, leaving 11 in the top. And so we get 7 times 11 over 55, which is 77 over 55. When we divide, okay, the key here is that we define division to be multiplying by the reciprocal. So a over b divided by c over d is defined to be a over b times d over c, which is a times d over b times c. So really it just boils down to, again, just rewriting these, but when you bring this over here, the first one always stays in the same order, but the one after the divides flips over. But then what are you really doing? You're still rewriting it in factored form and cancel. So really it's no more trouble than the other. You just got to remember where to write things. So 54 is 2 times 27, so that's 2 times 3 cubed. 65 is 5 times 13, so that goes over here. Notice the 189 is going to go to the bottom. It turns out to be 3 cubed times 7. And 1183 turns out to be 7 times 13 square. I kind of regrouped this in the top and wrote it in increasing order of the bases. 2 times 3 cubed times 7 times 13 square. And the bottom I rewrote is 3 cubed times 5 times 7 times 13. So I'm just putting these combining these together, adding exponents whenever they have the same base, and rewriting it as increasing order. And now what I'm going to do is just cancel out the things that match up. So no canceling on the 2's. 3's cancel out completely. 7's cancel out completely, but not the 5. And one of the 13's cancel, so we're left with 2 times 13 over 5. Clearly it's reduced in that form. And so 2 times 13 is 26. And so 26 is reduced. Reduced means the greatest common factor of the top and denominator is 1. This is also an improper fraction, so you could make it into a mixed number if you wanted to. But as far as a fraction, it's better in this form. There are times when we want a mixed number, and there are times when we would rather have an improper fraction. Here's another one where it's a combination of multiplication and division. We factor all 6 parts. Remember, the 1400 is going to go to the top, the 1053 goes to the bottom, but the 51 stays in the top, the 85 in the bottom, and the first one stays where it is. I sort of regroup things here so I keep track of it. 2 cubed, put all the 3's together, there are 4 of them in the top, and so forth, and then cancel out, and this works out to just be a half. Now, how about with polynomials? Turns out you get exactly the same setup here. Look at this. Same algorithm. The factoring just becomes factoring of polynomials. So the first one is just a reducing fractions problem. So I factor the numerator, factor the denominator, and then cancel. And that works out. We are assuming in the canceling that the thing we're canceling out is not 0. So in the next one I factor out. So 18 minus 50x squared, first of all I write it decreasing order as negative 50x squared plus 18. Notice it's a negative in the front, so I'm going to factor out a negative something. Actually negative 2 is the greatest common factor. That leaves you 25x squared minus 9, which factors as 5x plus 3 times 5x minus 3. So these first three factors are the first numerator. The bottom I can factor out a 4, which I want to think of as 2 squared really. And then x squared plus 2x plus 4, and that doesn't factor anymore. X cubed minus 8 is a difference of 2 cubes. X cubed minus 2 cubed. Bring the x down, bring the minus, bring the 2. Use the binomial to get the trinomial. Square the first, square the last. Multiply, but use the opposite sign for the middle. And the trinomial doesn't factor anymore. This one here is trial and error, or anti-FOIL factoring. It turns out to be 5x plus 3 times 3x minus 5. Let's see if we can cancel anything. One of the 2's cancels, leaving a negative 1 at the top, a 2 in the bottom. These trinomials cancel here. 5x plus 3's cancel as well. And so we're left with negative 1 times 5x minus 3 times x minus 2 in the numerator, and 2 times 3x minus 5 in the denominator. Here's one with multiplication and division. This one everything cancels out. It's just 1 in the end. Let's see if we can see that. X squared plus 4x plus 4 is x plus 2 squared. 3x squared minus 11x plus 10 is 3x minus 5 times x minus 2. So these two factors and these two with the square, or this one with the square on it, that's the numerator, and this is the denominator for the first fraction. X to the fourth minus 1 is x squared squared minus 1 squared, so that's x squared plus 4 times x squared minus 4. The x squared minus 4 further factors is x plus 2 times x minus 2. 2x squared plus x minus 6 factors is 2x minus 3 times x plus 2. And then the second fraction is going to flip, the last one, after the one right after divides, is going to flip over. So the 6x squared minus 19x plus 15 goes to the top, which in factored form is 2x minus 3 times 3x minus 5. And this trinomial here, you can factor this cubic, a fourth degree polynomial, you can factor by grouping, and it turns out to be x squared plus 4 times x plus 2. And then if you look at it, everything cancels out. There's 2x plus 2's in the bottom, here and here. They cancel with these two in the top. The 3x minus 5 cancels the one at the end. The x squared plus 4 cancels here. And then the x minus 2 cancels the x minus 2 here. The 2x minus 3 cancels here. If you ever get anything to cancel out completely, it's a 1. Everything in the numerator cancels, so it's a 1 in the numerator. Everything in the denominator cancels, 1 in the denominator. Of course, 1 divided by 1 is 1. And so this just everything canceled here. More examples for you to practice. Okay, and we will stop here. We'll pick up talking about adding and subtracting fractions a little bit in our next video.